I welcome all of you to the video lecture series on fluid mechanics. This lecture is on topic 2 on fluid statics. The title of this lecture 7 is pressure, which corresponds to the topic 2 on fluid statics. After the topic 1 on introduction to fluid mechanics. And before we move on to the topic of fluid kinematics and fluid dynamics, this lecture is on the topic 2 on fluid statics. This lecture is particularly focused on the first subsection of fluid statics, which is pressure. In fluid mechanics, commonly we encounter inertia forces, viscous forces, pressure forces, and gravitational forces. Among this, when the fluid is stationary, there is no rate of change of momentum, and there is no viscous resistance because the fluids are not flowing. So under this condition, the inertia forces and the viscous forces are zero, and we encounter only the pressure and the gravitational forces. So this lecture we will discuss about the pressure. After introducing the pressure, we'll move on to the Gavani equation for fluid statics and determine its solution for pressure distribution or pressure field in a stationary fluid. Finally, we'll consider a couple of engineering applications of fluid statics corresponding to first a manometer and secondly for a hydrostatic force on a submerged surface. So let us move on to the lecture on pressure. This will be presented first for pressure on a surface and then for a pressure at a point. So let us start the topic 2 on fluid statics. Before I move on to the details of this lecture on pressure, first I'll give you the brief introduction on fluid statics. After the introduction on fluid mechanics on topic 1, this topic we are considering fluid as stationary, and later on we'll move on fluid flow situations where we'll consider fluid in motion. When the fluid is flowing, if you consider a picture of fluid flow, then the actors of that pictures are the velocities and pressure. Whereas if you consider a stationary fluid situation, and if you talk about the actor in a fluid static situation, then you do not have a velocity since there is no flow, and you only have pressure as an actor for fluid statics. Let us start with every topic from now onwards. I'll start with certain learning objective, because whenever you take a course, you are expected to learn from that course. So these are the specific learning outcomes which is expected after you have gone through these topics and solved the assignment problem, which will be focused towards these learning outcomes. So the first learning which is expected after this topic is that you should develop an ability to present the direction of pressure firstly on a surface which could be within a fluid or over a solid surface. And you should also have the ability to know the direction of pressure at a point. So the ability for the direction of pressure is expected from this learning outcome. And the second learning outcome is you should develop an ability to evaluate pressure field in a stationary fluid. As I said, that in fluid static, pressure is like the actor in a picture of fluid situation, fluid in a stationary situation. Then, so in this case, for a stationary fluid, you should be able to evaluate pressure distribution. That's the second learning outcome. Final and the last learning outcome is that once you have evaluated the pressure field, as an engineer, you should be able to apply the effect of pressure distribution that is encountered in various engineering applications. Two such applications will be discussed here. First, for a manometer, which is a pressure measuring device, and the second on hydrostatic force on a submerged surface. When you consider the force which is generated by air, we call it as an aerostatic. When the force is generated by a liquid, we call it as a hydrostatic. So when the fluid is stationary, when the liquid is stationary, it generates certain forces which will be discussed in this topic. Hydrostatic force on a submerged surface. Now let us move on to, so these are the learning outcomes which are expected from you. You should develop certain ability and you should be able to evaluate, and finally you should be able to apply what you learn from the characteristics of the pressure distribution. So let us get started with the title of this lecture. The title of this lecture is pressure. And as I had mentioned that you should know from this topic, learn the what is the characteristic of pressure when it acts on a surface. When I say on a surface, it could be two types of surfaces. It could be a surface within a fluid, stationary fluid, or it could be a surface which is a solid. So the fluid which is in contact with a stationary fluid which is in contact with a stationary surface, then what is the direction of force on that surface? So for those two cases, the direction of pressure will be discussed here. And secondly, the pressure at a point, what is the direction, it will be discussed here. So I would mention that the pressure on a surface acts normal to the surface, whether it's a fluid surface or a solid surface, and it is compressive, it is inward force. It's a normal and compressive force, and pressure is defined as force per unit area. So it's a normal and compressive force per unit area. Whereas pressure at a point, later on I will show you the derivation, but just to point it out, pressure the magnitude of pressure is same in all the directions. All of you know that for a vector quantity, the magnitude changes with the direction. So since the magnitude of pressure is same in all the directions, it's a scalar quantity. We have defined fluid in the previous topic that fluid cannot sustain a shear force. So since a fluid deforms continuously, the continuous deformation, you can call it as an onset of flow, under the action of the shear force. As I said that we have defined fluid which cannot sustain the shear force, so it deforms continuously, and that deformation continuously we define as onset of flow. But in stationary fluid, there is no onset of flow, so the shear force should be absent. So a stationary fluid cannot have a shear force acting on it. So the only possibility is it can have a normal force. Thus only a normal force acts on a surface within a fluid or on a solid surface. The normal force per unit area, note that it acts inward to the surface, and we call that inward force as compressive force. So this is a justification that in a stationary fluid, you cannot have a shear force. The only possibility is a normal force, and that too, it acts inward to a surface. Now I will demonstrate the application of the pressure on a fluid surface as well as a solid surface. So let us take surface of a fluid and a solid. So we are taking a surface of a fluid within a fluid, stationary fluid region. So let us take a fluid region or element which we call as fluid control volume. This is an elemental control volume which is shown of square shape of size delta x and delta y. And let us consider the pressure force at three different points A, B, C on a tank which is shown here, which is filled with water. So we are showing 4 points on this fluid surfaces, 1, 2, 3 and 4, and the pressure is shown here. On vertical surface, the pressure is acting in horizontal direction. On vertical faces, you can see the pressure is acting in the vertical direction. Horizontal surface, vertical direction, vertical surface, horizontal direction. And in all these cases, the sense of the arrow is inward. So all this, the pressure acts normal and compressive for a surface within a fluid, stationary fluid. Whereas if you consider a fluid, here in this case, water, which is in contact with the surface of the tank, three different points have been shown, A, B and C. And in all these surface points, you can see that the pressure is acting normal and inward. So this is a representation of pressure on a solid surface And this is the representation of pressure on a fluid within a fluid region, represented here by a fluid control volume. Here it is represent the direction of pressure on a surface is represented for a stationary fluid, but note that this is also applicable for fluid in motion, which will be discussed in the later topics. Now let us move on to the derivation, which will demonstrate that the pressure at a point is same in all the directions. So to prove this, let us take a triangular elemental control volume of width delta x, height delta y, and the hypotenuse of the triangle is of length L. Let us consider the dimension of this element perpendicular to this plane as unity. Now, on this fluid control volume or a fluid surface, now we will show you the pressure force. So the pressure force will be, the force due to pressure is given by the product of pressure and surface area, because pressure is a normal compressive force per unit area. So we have to multiply by the surface area. The surface area of this vertical surface is delta y. So this will P1 is multiplied by delta y. And the horizontal surface width is delta x. So P2 is multiplied by delta x. And the length of this hypotenuse is L. So this P3 is multiplied by L. So these are the pressure forces. When the fluid is stationary, there cannot be a rate of change of momentum. So the inertia force is 0. And there cannot be any viscous resistance because there is no motion between the different layers of a stationary fluid. So the only forces which acts are, as shown here, are the pressure forces, but along with the pressure, you know that there will be a gravitational force which acts. Gravitational force is equal to the mass of this control volume multiplied by the acceleration due to gravity. So this is the density, this is G is the acceleration due to gravity, and the volume of this control volume of this triangular fluid element is delta x into delta y divided by 2. So considering the balance of the pressure and the gravitational force, if you apply the Newton's second law of motion, the rate of change of momentum is equals to force. Since fluid is changing, rate of change of momentum is equals to 0. So only there is a force balance. So you have to balance the horizontal and vertical component of this pressure force and the gravitational force. So let us suppose we take the first condition, sigma fx equals to 0. So applying the force balance, sigma fx equals to 0, you end up with, so if you take the, note that this pressure, this in this triangular control volume, this angle is theta. So the angle of this pressure P3 with a vertical line is theta. So if you want to take its horizontal component, you have to take multiply by P3 sine theta, P3 into L sine theta, which is equal to delta y. So you get P1 is equals to Py, P1 is equals to P3, sorry. And when you take sigma Fy is equals to 0, then the gravity force will come into expression. And when you apply limit delta x delta y tends to 0, you end up with P2 is equals to P3. So from this you get P1 is equals to P2 is equals to P3, which means the pressure is same in 3 different directions. You can see that the pressure, when you apply limit delta x delta y tending to 0, this control volume reduces to a point, and then you can realize that this pressure at a point, which is this pressure force is acting in the horizontal direction, this is acting on the vertical direction, this is acting on an inclined directions. So in all these 3 directions, since the magnitude of the pressure is derived here as same, so the pressure at a point is same in all the directions, and it's a scalar quantity. Note that when you apply sigma Fy is equals to 0, you have to take the vertical component. So this will be P3 into L cos theta, and the gravitational force will also appear. So you have, this is the pressure vertically upward, this is downward, and this is the gravity force which acts downward. And when you apply delta x delta y tends to 0, you get P2 is equals to P3. So using this two, you have derived that these pressures are equal. After this derivation, let me show you when we measure the pressure at a point, how do we define? We have to use some reference with which we define a magnitude of a pressure. So there are two commonly reference which are used in the literature. If you measure the pressure with respect to vacuum, then we call that as absolute pressure, as shown here. Whereas if you measure the pressure with reference to the atmospheric pressure, this is shown here as atmospheric pressure. So if you take absolute pressure minus the atmospheric pressure, which is shown here, this is called as gauge pressure. So gauge pressure is a pressure where the datum or the reference which you are choosing, this is a commonly we use. We many a times talk about the magnitude of pressure with reference to an atmospheric pressure, and this is called as gauge pressure. If this gauge pressure is negative, then we call it as a vacuum. With this, I had come to the end of this lecture on pressure of the topic 2 on fluid statics. These are some of the reference books for this topic. Thank you for your attention.